Welcome back. This is sub-module 2 of 3 on survey tools and technology. So far we have covered the various types of surveying tools used in directional drilling. These range from inclination-only devices to high-accuracy gyros and MW-DLWD systems. Second, you'll understand the sources of magnetic survey errors, including drill string interference, crustal field variations, and magnetic variance. Next, we will look at how to calculate non-magnetic component requirements for a BHA, ensuring survey instruments are isolated from magnetic interference. Finally, we will briefly describe the commonly used surveying tools, state when each is most effective, and explain their similarities and differences. So let's continue. To combat interference, magnetic survey tools are housed in non-magnetic drill collars, NMDC. These collars are made from non-ferrous alloys, often non-magnetic stainless steel, which provide the required strength while not distorting Earth's magnetic field. By isolating the survey instrument inside a sufficient length of NMDC, we shield it from the magnetic influence of the ferric drill string above and below. It's important to remember that in this context, magnetic refers broadly to any tool that relies on measuring Earth's magnetic field. MWD systems, steering tools, and multi-shots all fall into this category. If they are placed inside standard steel drill collars, the readings will be compromised. The required NMDC length depends on factors such as hole inclination, azimuth, and latitude. For example, wells drilled east-west and at high inclinations need longer non-magnetic spacers because errors are amplified in these geometries. The message is clear. Whenever magnetic tools are used, adequate non-magnetic collars must be included in the BHA design. Skipping this step is not just a technical oversight, it creates systematic survey errors that cannot be corrected after the fact. Calculating magnetic isolation is a complex yet essential process. The goal is to determine how much non-magnetic spacing is needed to keep the predicted azimuth error below a set limit, often 0.25 degrees. The calculation considers multiple variables. The interfering magnetic field, IF, generated by BHA components, the pole strength, LP, of stabilizers, bits, motors, and drill collars, and the total earth field strength, H, in the drilling location. It also accounts for azimuth, inclination, declination, and dip angle of the well. Length parameters, X, Y, Z, B, and C, define non-magnetic and magnetic material distances relative to the survey tool. For example, stabilizers and bits typically contribute 77 to 260 units of pole strength, while mud motors can exceed 860. Using these inputs, software or manual formulas estimate the azimuth error AE. If AE is above tolerance, additional NMDC length must be added. In practice, service companies run these calculations with proprietary software, such as SLB's EDI module in Drilling Office. The outcome is a clear recommendation: how many feet of non-magnetic collar are needed above and below the tool. This ensures that survey data remains within acceptable accuracy for safe, effective directional drilling. Let's examine the top formula. IF is the interfering field. The components are made up of the amount, a constant 770 divided by the square of the distance of non-magnetic material above the survey sensor, plus the pole strength of the components below the MWD divided by the square of the combined length of non-magnetic material below the survey sensor, subtracted by the pole strength of the magnetic components or tools below the MWD divided by the square of the total length of non-magnetic and magnetic material below the survey sensor. The calculation for the interfering field is then substituted into the calculation for the predicted azimuthal error due to the interfering field. Because drill string interference is the largest contributor to magnetic survey errors, service companies have developed software tools to predict and mitigate it. One common example is SLB's Estimated Drill String Interference EDI calculator, which is part of the Drilling Office suite. These programs model the BHA, accounting for the number and type of steel components, their positions relative to the survey tool, and the drilling geometry. They then calculate the predicted magnetic interference and estimate the resulting azimuth error. The goal is to keep the error within acceptable limits, typically less than 0.25 degrees. If the predicted error exceeds this, the software will recommend adjustments, most often adding extra non-magnetic drill collars, NMDCs. The beauty of this approach is that it removes guesswork. Rather than relying on rules of thumb, engineers can simulate the actual magnetic environment and optimize the BHA design before drilling begins. This not only improves survey accuracy, but also reduces the risk of costly redrills or anti-collision incidents. The key message is that modern drilling demands predictive modeling. Without it, survey accuracy is left to chance, and in today's complex wells, that's unacceptable. Let's move on. The Topco tool is one of the earliest and simplest survey devices designed to measure only inclination. It works by punching small holes into a wax-coated cardboard disc, marking the angle of deviation. Typically, the tool was dropped into the drill string, go deviling, and later retrieved on a trip. While crude, it provides two key benefits. It was inexpensive and offered a quick check on well verticality. The Topco became popular for simple vertical wells, where precise azimuth data was not needed. It gave drillers a way to confirm that the well had not strayed excessively off course. Its limitations were obvious. It provided no azimuth, could not be used in real time, and required retrieval to analyze the results. Still, for its time, it was revolutionary, representing the first practical step toward wellbore surveying. Today, it is largely obsolete, replaced by electronic inclinometers and MWD tools, but the Topco remains a useful teaching example of how the industry's earliest survey methods paved the way for modern real-time systems. It highlights the progression from mechanical, after-the-fact surveys to continuous digital measurement. The Topco tool comprises a timer, an inclinometer, and a clockwork punch. The working parts are placed inside a barrel and dropped in the hole, landing on a special ring in the BHA. When the timer goes off, a small hole is punched in the paper disc. Then the disc rotates half a turn and another hole is made. These two holes should be about 180 degrees apart and should show the same reading. The Topco is often dropped just before a trip out of the hole as a check in a vertical well. It can alternatively be dropped down the string and fished on wireline, or run and retrieved on wireline. If you look closely at the green disc, you can make out the two punched holes. I have circled them in blue to help. The disc shown indicates an inclination of about 3.5 degrees. In land wells, the top sections are often short and vertical and are drilled with two runs due to the bearing life of the insert bits used. At the end of the first run, prior to pulling out of the hole, a Topco is dropped to check for verticality. The Topco system consisted of a survey barrel and running gear. The inclinometer and timer were assembled into the barrel, which was then deployed by go-deviling or slickline. The tool relied on simple mechanics. As drilling paused, the device recorded the inclination by punching a mark onto a wax disc. These discs provided a permanent, low-cost record of well deviation. To operate effectively, the Topco required specialized running gear such as survey baffles and float valves to ensure proper placement. While not precise by modern standards, the Topco filled a critical niche in the 1950s to 70s. It allowed operators to verify verticality without expensive wireline surveys. Its simplicity also meant it could be run by rig crews without specialist training. However, Topco surveys were limited by inclination-only readings, susceptibility to human error in interpretation, and time delays. Valid surveys typically showed incremental deviations, with discs perforated at standard card angles such as 8 degrees or 16 degrees. Although now a relic of drilling history, Topco's value lay in its practicality and affordability, showing that even simple tools can significantly improve drilling outcomes. As no directional control is available, as the survey tools cannot measure azimuth, there is no requirement to orient the tool with the BHA, so a simple baffle can be used to land the tool in. As the tool is not affected by magnetic interference, it is often possible to take a measurement from just above the bit. In this case, a spider can be installed on the float valve in the bit sub to get the required measurement. In the picture, you can see two paper discs. The disc on the left has circles that graduate by 1 degree. On the right, the circles graduate by 2 degrees. I need to make sure you use the correct paper for the tool. The underdrift and teledrift tools represented the next step beyond TOTCO. These devices measured inclination mechanically while drilling, sending the results to surface via pressure pulses visible on the standpipe gauge. The system worked by housing a spring-loaded mandrel in a sub. As the pump started, the mandrel moved downward, and a bob engaged grooves machined at different inclination angles. Each groove generated a pulse as the mandrel passed, with pulse counts corresponding to inclination values. Tools could be calibrated for 0.5 degrees or 0.25 degrees increments. The advantage of underdrift and teledrift was that they provided a free survey. No extra trip or retrieval was needed. As long as the pumps were running, the driller could monitor the inclination in real time. This made them far more efficient than TOTCO. However, they still had limitations. They gave inclination only, with no azimuth, and accuracy was limited by mechanical tolerances and pulse interpretation. Nonetheless, these tools were widely used before electronic systems became standard, representing an essential bridge between early mechanical devices and modern MWD systems. They showed that real-time surveys were possible and desirable, even if initially crude. The underdrift tool is taken on rental. It will cost a few $100s a day. The vertical part of the well gives a free survey on every connection. As seen in the animation on the bottom right, when the pump is switched off, the tool resets itself. An inclinometer in the tool positions the working parts in a position which is related to the inclination. When the pump starts up again, the tool sends up pressure pulses, which can be seen on the pressure gauge by the driller. The number of pulses is counted, and this count indicates the inclination of the tool. It's preferable to running TOTCO surveys, as it eliminates the risk of a broken wire line in the string and takes only a few minutes compared to perhaps half an hour for a TOTCO survey. In this section so far, you should now be able to list the various types of surveying tools used in directional drilling, from inclination-only devices like TOTCO. You should also be able to identify the sources of magnetic survey errors and explain why drill string interference accounts for most of the inaccuracies. We then explored how to calculate non-magnetic component requirements for a directional BHA, ensuring survey tools are shielded from magnetic distortion by sufficient non-magnetic drill collars. In the next and final submodule, we will conclude the discussion on commonly used survey tools, explain when each is most suitable, and outline their similarities and differences. So let's continue. That brings us to the end of submodule 2 of 3 in the Survey Tools and Technology module. Please progress to the quiz, then on to the last submodule on Survey Tools and Technology. Thank you.